Hello, welcome back. This is Cal 2, section 9.2. Let's see, I talked about the nth term test or divergence test for series. This is where we start talking about series a lot in 9.2. There's also the big concept of geometric series. We did talk about this a little bit before the break, but I just wanted to remind you here. So if it's a geometric series, it looks like this. It sort of comes in this form, although sometimes the algebra looks a little different. But when it comes in this form, what that means is if you plugged in 0 and started looking at these terms, the first term would be a, then a times r, then a times r squared. And so what makes it a geometric series is the fact that each time you get to a next term, you are multiplying by r. Or to get from one term to the next term, you multiply by some common ratio called r. And here's the truth. If this is an infinite series, but if r is less than 1, the absolute value of r is less than 1, r could be negative. By the way, what that means is r is between 1 and negative 1. Is what the absolute value of r less than 1. Then the series converges, and that kind of makes sense. You're multiplying by something less than 1. The terms are getting smaller. It will converge. Now wait a minute. Not everything where the terms get smaller converges. But this one does. A geometric series will. If r is greater than 1, it also makes sense. You're multiplying by something bigger than 1. These terms will grow, and what they add up to is infinity. So the series diverges if r is greater than or equal to 1. So we should know these rules about a geometric series. By the way, if it converges, we have a cool formula to tell me what the infinite series converges to. It converges to a over 1 minus r. Notice, though, this a is the first term. So be careful. This definition is the first term. In fact, I've got one example here I wanted to do to just test you here real quick. This is kind of easy. An infinite series looks like it's in the proper form to be a geometric series. Looks like I've got this 100 is my a, and I've got this r is 0.9. So if r is 0.9, looks like a geometric series. R is 0.9, that's less than 1. This geometric series converges. This is kind of what I expect you to explain to me. You tell me out loud, it's a geometric series, in writing. It's a geometric series. You identified r is less than 1. Basically, by the rules, you know it converges. Not only that, though, please don't stop there. When it converges, please tell me what it converges to. And so I'll use this little formula. But notice that this one starts at 1. And because it starts at 1, that a, that's not the first term. When it starts at 0, a is the first term. But when it starts at 1, well, let's plug it in and see what the first term is. When it starts at 1, I plug in a 1, I get 100 times 0.9. Oh, the first term is 90. So the sum of the series is the first term over 1 minus 0.9. That's the formula, the first term a over 1 minus r. Okay, what is that? 90 over 0.1, and that happens to be 900. This series, infinite series, here it is. This infinite series adds up to 900. I'm going to erase this now. That was just an easy example. And I want to do, what I like to do is these word problems. So, there's not too many. There's an example in the book. I'm going to erase this. That problem's over. We found out what it converged to. And then there's a little, kind of a nice, I like to do applications of geometric series. They're kind of easy, although it's a funny application. This one says that a ball drops 20 feet. And it's one of those really bouncy balls. So when it drops 20 feet, it bounces up to 3/4 of its height. I'm going to say it bounces up to 0.75 of 20 feet. And then it falls, and then it bounces back up to 0.75 of that. And it bounces back up, and it bounces back up. Every time it bounces, it's 0.75 of the previous height. So the question is, this does this forever, infinitely, and the question is, what is the total vertical distance traveled by this bouncing ball? What is the total vertical distance traveled by this bouncing ball? Well, it's a geometric series. But it takes a little thinking, a little bit of work. You know, what I like to do is just think about the down distances. And if I just think of the down distances, because they did say the total vertical distance, so I do have to count the ups and the downs, but let's worry about the downs for now. The first down is 20. The next down is 0.75 times 20. The next down is 0.75 of that, which I think is 0.75 of 20. Yeah, 0.75 squared of 20. The next down is, I think I can write a series for this. It starts at 20. You multiply by 0.75 every time. That would be a geometric series. It starts at 20. You multiply by 0.75 every time. Then that geometric series starts at 0 and goes to infinity. Now those are just the down distances. You know, if I want all the up distances, then I should, maybe I should double that. Yeah, double that. I get this down distance and then double it for that up. That down distance, double it for that up. So I should double this, but the problem is I just doubled this 20 and I don't want to double the 20. So now I've got 20 too much. So I think I'll subtract 20. That's the answer. The down distances doubled to get the up distances, but you did 20 too much. Subtract 20 and you've got it. Well, it is a geometric series. It does converge. R is 0.75, but what does it converge to? We can use our little formula here. It converges to the first term is 20 over 1 minus 0.75. That's what it converges to. I'm going to multiply that by 2, and then at the end I'm going to subtract 20. Working my way into a little corner down here. Let's see, that's 20 over 1/4. That's an 80. 80. That's 80. 20 divided by 1/4, or 0.25. Yeah, that's 80. That's multiplied by 2, and then I should subtract 20. Well, everybody knows that's 160. Subtract 20, 140. 140 feet is the total distance traveled by this infinitely bouncing ball. All right, thank you guys very much. I'm going to move on into the rest of chapter 9 here shortly. This is some of the ideas we talked about before the break. You should be working on homework, working on that quiz. All right, thanks.